A few videos ago, I built this compact LEGO 7-segment display, and now I want to make several major improvements to it before I connect multiple of these together to make a counter. First off, with how the design currently stands, when I turn the programming wheel to make the display count up through each of the numbers, there is far too much resistance within the mechanism, especially on some of the numbers where the wheel has to push back a lot of the pins all at once. So far, I've been using these two rubber bands to hold all the segments in their default positions until the pins push them, with extra rubber bands here and here, specifically to hold those two segments in place. Otherwise, when the two pins adjacent to either of those get pushed back and stretch the rubber bands away, the segment between them would be free to move too, so the extra band helps to hold it in the right position. It is important that there is some kind of opposing force to hold the segments in place, but using all of these tight rubber bands makes it really difficult to turn the programming wheel. With just a single display, I don't have too much trouble turning it manually, and a motor would most likely be able to turn it as well, but since I'm planning to connect 4 of these displays together, the combined resistance of all of those would be far too high. I showed in my previous video on this that relying on gravity to pull the segments back wouldn't be a reliable enough solution, so I had to look at some other rubber band options instead. Since there is almost no friction when moving the segments, we really shouldn't need to apply much force at all, but these official LEGO rubber bands are very stiff and short, and therefore they add an unnecessarily high amount of resistance into the system. Instead of those, I found these ones which have a much lower stiffness and are the perfect size to cover the whole height of the display. And to reduce the resistance even more, instead of pressing both strands of the rubber band against the pins, I made it so only a single strand pushes there, and the other one is held to the side. Unfortunately, the 2 supplementary rubber bands had to stay on to make sure those segments stay in place, but I made them as loose as I absolutely possibly could to minimize their contribution to the total resistance. Altogether, this did an incredible job of making the wheel easier to turn. Using this torque measurement mechanism that I designed last year, it showed that the peak torque needed to turn the programming wheel went down from roughly 5 Newton centimeters all the way to 3 Newton centimeters, which is a really substantial drop-off. Next up, I saw a lot of suggestions to replace these teeth on the programming wheel with plates with towels on them instead to push on the pins. And at first I was a little skeptical, thinking that maybe the towels would stick out the wrong distance or the plates and towels would break off more easily, but no, this turned out to be a bigger improvement than I could have ever imagined, and in more ways than one. Firstly, it's much more reliable. On the old design, the teeth would fairly often come loose or fall off, or twist out of position so they don't push properly on the pins, or sometimes the whole tracks would come off. In contrast, the towels on the new design proved to be far more robust and consistent. They also helped out in a far bigger way than just that. You see, on the old design, once the display switched over from one number to the next, all 7 segments would be showing again briefly, which made it misleadingly look like it was displaying a number 8 for that time. Then there would be this long transition region over which the teeth would slowly push the pins back to display the correct next number, a number 1 in this case. And by the way, the segments are on by default, with the teeth pushing on the segments to turn them off. As I explained in that previous video, that was another method I used to reduce the resistance, as the segments on average need to be pushed on a lot more than off. But because of this really large transition region between the numbers, where it looks like it's displaying an 8, it did mean that the segments being on by default detracted a lot from the clarity of the display. But this was entirely the fault of this really bad programming wheel design. With the new design and how much thicker these rounded towels are compared to the teeth of the old one, there is a far smaller transition region between each of the numbers, and the pins of the next number start getting pushed back almost right from the moment they're released from the previous number. All of this means that the display now far more clearly shows each of the different numbers, and that the segments snap directly from one number to the next. I'd like to emphasize that this isn't just thanks to the smaller transition region between the numbers, but also the fact that the towels on the wheel are pushing the pins into their furthest back position and holding them there for a much longer time while the wheel rotates past. This results in the segments being discernibly either on or off for most of the duration of each number. In contrast, on the earlier design, the teeth would very slowly and gradually push on the pins, resulting in the display really slowly fading into the right number, before snapping back to showing an 8 again. And even worse than that, because of the angle the teeth make with the pins, the force of the rubber band being stretched was acting to push the programming wheel backwards the whole time. This meant that turning it was basically like balancing on a knife edge, where you want to push the pins back as far as possible to properly display the number, and you need to apply constant pressure to keep them there, but if you go just slightly too far, it snaps over to the next number, and there's no going back. That's why in the previous video I had to make this special ratchet mechanism to hold the programming wheel just at the perfect point where it would clearly show the numbers. And heaven forbid I tried to turn it with any reasonable speed, as it would overshoot right past the pins and go to the next number. But to my absolute amazement, all of this was completely solved by the new design. Not only do the tiles push the pins back all the way almost immediately, but the angle that the pins make with the tiles means that they get fully locked in place when they get pushed back. So I can take my hand away and the pins all stay perfectly in place to display the correct number. No ratchet needed. This locking action of the pins also lowered the resistance of turning the programming wheel even more compared to the old design. I thought I'd show the versions with the old and new programming wheels side by side here to really help to illustrate how much more clearly the numbers are presented on the new design. And given how much quicker the new design snaps between each of the numbers, I wanted to show what happens if I go back to having the segments being off by default, with the tiles pushing on the segments to turn them on. For one thing, you can see that we need a lot more tiles on the programming wheel, which will add more resistance. Comparing the two methods, I was expecting to be able to say that both displays look very similar because the segments toggle very quickly from one number to the next, but the performance of the off by default display actually turned out to be a lot worse. This was because the rubber bands turned out to be doing a much worse job of bringing the pins back into position after the wheel had pushed them. This seemed to be the result of more of the segments needing to be pushed back all at once, which pushed the main rubber band out of the way so it couldn't hold the remaining pins in place. But even without this problem, keeping the segments on by default is still very beneficial. Dusting off the old torque measurer once again, it showed that having the segments on by default reduced the resistance by almost half compared to the segments being off by default. And that will be really important for what's next, which is connecting a whole bunch of these displays together to make a counter. I've got to say, seeing all four of these displays next to each other like this does look very cool. And even just with two displays, the camera doesn't really do justice to just how many layers of mechanism are packed within there. I also find it pretty fascinating to watch the displays counting up through the numbers without any of the tiles on the front, so you can really see all of the linkages at work. It turns out that I needed to add a third supplementary rubber band specifically to hold this segment in place, but luckily there was somehow enough space to fit it in, and I managed to keep it nice and loose like the other ones so it wouldn't add too much to the total resistance. You can see that I needed to cut a lot of these strips to the correct size and shape to use for all of the segments, and I feel like my process of doing that taught me a valuable lesson in quality control. When I was cutting all of the strips, I cut a whole batch of them all in one motion to try and give each strip a consistent width, but since I was doing this by hand, there was of course going to be some variation in their widths. Like with any production line though, these followed pretty close to a normal distribution, with only a few outliers at the tail end that were either unacceptably too narrow or too wide, and meanwhile the bulk of the strips were all well within the margin of error that I was happy with, so I could use all of them to stick onto the displays. And when doing this, it made it a lot easier that the segments were all on by default, as it meant I could stick the strips directly onto the parts already showing, instead of having to manually hold them in their on positions. Attaching all of these displays together also made me want to try replacing these sections of tiles on the front, which could break off quite easily, with this large panel to cover all the displays. The single panel design was the product of a lot of compromises, so I wanted to see if I could do something better now that I was working with multiple displays. Since it wasn't possible to have any stud connection points anywhere besides the very top and bottom, these side tiles had to be attached on only from right at their edges. This meant that if the side segments flipped back with too much force, they could start to nudge the tiles off a bit. I considered using 2 layers of plates to span the full height, but that really obscured the view of the segments when viewing them from any angle other than directly head on. Now that I was working on multiple displays, it meant I could use these 2x16 plates instead, which could be fixed from both the top and the bottom. The big downside here is that the studs are showing, but there aren't any tiles LEGO makes that are this long, and putting tiles on top of the plates would again start to obscure the view of the segments. After seeing it in person though, I decided that I liked the look of the individual panels a lot more, so I went back to those, but since I could now connect all of them together, they were a lot less likely to break off. For the moment though, I'm actually going to leave them off so we can more clearly see what's going on while I try and couple these displays together. My first idea to connect adjacent displays was to use a stepper mechanism. This makes the output step forwards only in 90-degree increments. I connected this to each of the programming wheels with a 2.5:1 gear reduction. This means that each time the programming wheel of this display completes one full rotation, it will shift the programming wheel of the next display by exactly 1/10 of a rotation, which moves it precisely from displaying one number to displaying the next. In theory, this would be the perfect solution, but in practice, the stepper, the yellow piece, was rarely moving the correct amount when the red dial pushed it, and it would often get stuck between the two numbers. That was despite the alignment mechanism of the stepper trying to push the yellow piece the full 90 degrees into the correct position, as it was having to work against the whole resistance of the mechanism below. And by the way, there wouldn't have been any problem fitting multiple of these mechanisms next to each other for the subsequent displays. I would have just needed to alternate between high and low ones so they don't collide with each other. There is a more reliable form of a stepper mechanism called a Geneva mechanism, but I knew it wouldn't be possible to make one of those out of Lego small enough to fit between the displays. But perhaps I'm overcomplicating all of this, and it would be better to just connect the programming wheel of each display to the previous one with a simple 10:1 gear reduction. That's what a lot of people were suggesting in the previous video, but I was a bit hesitant to do that because it means the programming wheels will be turning at a constant speed, rather than shifting straight from one number to the next. With the old pad programming wheel design, the transition region between each number accounted for roughly 80% of the total arc that it makes, meaning that if the programming wheel is turning at constant speed, the display would only be showing an actual number 20% of the time. With the new design, that transition width, where the segments are jumping between the two numbers, accounts for about 40% of the total arc, meaning that the display stays settled on the correct number for roughly 60% of the arc that the programming wheel makes. That's certainly better than before, but if the programming wheel is rotating at constant speed, it still means the display will only be fully showing each number for 60% of the time. So let's say we have two displays connected with a 10:1 gear reduction behind them. So this is the units counter and this is the tens counter. If we say the units counter is counting up one number per second, then it will be spending 0.4 seconds transitioning between each number. But since the tens counter is counting 10 times slower, it will be transitioning between each number for a full 4 seconds, and then hold on that number for 6 seconds before transitioning to the next one. Here's what that process looks like with the numbers counting up a lot faster. You can see that the transition region for the tens counter lasts a lot longer than it does for the units counter. And now I'll factor in the hundreds counter with another 10:1 gear reduction. Since this counts 10 times slower again, if we were saying the units counter would count up one number per second, then this hundreds counter would be taking a full 40 seconds to transition between each number, and then hold on those numbers for 60 seconds. And then for the thousands counter, it will take 10 times as long again. So when it finally does count up to 1,000, you'll see that the fourth digit will take a really long time to switch from 0 to 1. In fact, it will take all the way until the first 3 digits count right the way back up from 0 to 400 for the fourth digit to update from showing 0,000 to 1,000, which isn't great. I do think though that this still does a really great job of showing the reliability of the displays, given that the first digit counted up through over 2,000 numbers without getting stuck a single time. This good reliability is certainly thanks to all of those improvements I made at the start of the video, but given how many moving pieces there are here, it still really surprised me how smoothly these displays run. But I still needed a way to make the displays transition faster from one number to the next. So I needed a mechanism to make the programming wheels jump more quickly between the numbers, as opposed to turning at constant speed. I realized that the primary issue with the stepper mechanism was that the input and output weren't directly connected most of the time, leading to the inconsistencies with the stepper not turning the correct amount. Of course, using gears can prevent this, since they are always in direct contact and will never fall out of sync, but I needed a way to make the output move faster some of the time and slower at other times. I was actually considering oval-shaped gears for a while, but I came up with a more effective solution. It was all thanks to the humble differential. You can think of the differential housing as taking the average of the speeds of the two inputs that come into it. So if both axles are rotating at the same speed in the same direction, then the housing rotates at that same speed as well. But if the inputs rotate in opposite directions, again at the same speed, then their rotation cancels out, and the differential housing doesn't move at all. But we do want the output to gradually move forwards over time, but we want it to do it in waves instead of at a constant speed, To do this, we can have just one of the inputs rotating at constant speed, and then superimpose on top of it rotation back and forth at the other input. This results in the output being stationary at the times when the two inputs are rotating in opposite directions, and then the output jumps forwards at the times when both inputs are rotating in the same direction. And since all the pieces here are connected with gears and linkages, there's no risk of anything falling out of sync or becoming misaligned over time. The first input completes one full rotation in the time it takes for this linkage to move back and forth once. So in order to cancel the housing's rotation exactly to 0 during the slow sections, I had to make it so the second input rotates roughly half a rotation forwards and then half a rotation backwards. If the second input rotated back and forth by less than that, the output would only slightly slow down and speed up. However, making the second input rotate so far meant I had to use all of this extra gearing. If I had just connected it rigidly to this linkage, it would only rotate back and forth by a small distance, and making this linkage rotate a full half rotation wouldn't have been possible. I realized that if I attach a pair of gears onto the linkage and hold the top gear stationary, then the relative motion of the gears to the linkage makes the axle rotate a larger distance than it would otherwise. So not only does the axle turn because the linkage is rotating, but also because the gearing on the linkage is rotating, so we're basically doubling up on the rotation. And then I realized that I could squeeze even more rotation out of this by using a higher gear ratio between the gears. Using this combination of gears gave the best results for bringing the output speed down to 0 during the slow sections. If I'd used an even higher gear ratio, the output would actually start to rotate backwards during the slow sections, and then move even faster forwards during the fast sections. Here are all 4 of them next to each other for all 4 displays. You can see why it was really important to make the design as compact as possible so they can all fit side by side like this. This mechanism was also incredibly convenient for creating the required 10:1 gear ratio from one display to the next. The common LEGO gears make it easy to create 5:1 and 3:1 gear reductions, but there's no single pair of gears that gives a 10:1 gear reduction. So the next best option would be to use a 5:1 and then a 2:1 gear reduction. The problem is that all available 2:1 gear ratios go off axis like this, which makes them really tricky to use to connect to multiple displays that are all in a straight line. With a differential though, when one of the inputs is fixed in place, rotating the other one makes the differential housing rotate at exactly half that speed, giving us the required 2:1 gear reduction without going off axis. And even though in this design the second input is rotating, since it's rotating back and forth equal amounts over time, it's equivalent to if it wasn't rotating at all, and the output on average still only moves half the distance of the first input. So I then followed that up with a simple 5:1 gear reduction to give the full 10:1 reduction I needed between subsequent displays. The gearing also worked out perfectly to be just the right width to line up with the spacing of the displays. You can see as well that there's just enough space to where the linkages at the bottom don't collide with each other. So let's try it in action. Since the differential housings are only rotating half of the time and are stationary for the other half, the displays now only spend 20% of their time transitioning between each number, as opposed to the 40% of the time they spent before. And while this is a big improvement, you can see that the hundreds and thousands counters still take a relatively long time to transition from one number to the next. To improve the design more, I'd need to make it so the differential mechanism jumps forward in an even shorter period of time, and then spends even longer stationary. To do this, instead of using a linkage that moves back and forth during equal times, I would need one that moves really quickly forwards, and then much more slowly and gradually backwards. If you imagine the motion of the simple linkage being represented by a sine wave, then whereas changing the gearing before was like changing the amplitude, here we would need to change it to make the peaks shorter and the troughs longer. Finding a linkage to do this was easier said than done. I tried out quite a few different designs for this. Most of these took inspiration from a reindeer automaton I made a few years ago. On this, I had to make the legs look like they were kicking backwards, so the linkages beneath had to move really sharply backwards and then more gradually forwards. I tried out a lot of different variations of this design, but none of them made much of a noticeable improvement compared to the standard linkage. I was looking online for some inspiration, and I found a mechanism that was used in a great ball contraption to make a big wheel only rotate part of the time. I had my reservations about whether I'd be able to make one of these compact enough to fit between the displays, but I thought I'd test it out regardless. On this design, the wheel is stationary 25% of the time and then rotates for 75% of the time, which means it's actually spending even more time rotating than the other designs. To solve this, I ran the input and output of the mechanism through a differential, with this axle here being the new output. This way, instead of the output rotating 75% of the time, it spends 75% of the time cancelling out the rotation of the input, and it's only during the remaining 25% of the time that the output actually moves. It does feel a bit gimmicky, but technically speaking, it is an improvement. But when I tried loading the output at all, it unfortunately broke the design. Since the movement of the output is now being resisted, the rotation of the input is being redirected through the differential into the big wheel, which makes it start to rotate backwards. And this causes it to collide with the dial, which makes it get completely stuck. And even if it had worked, this mechanism had no chance of fitting between the displays, and even those other linkage designs would have been unlikely to fit. So I decided to stick with the current design. I know it does mean the higher number counters will take a bit of time to switch, but given how perfectly this design fitted in alongside the displays, and that I couldn't find a better solution, I decided this was the best option here. A big reason for me focusing so much on the consistency and reliability of this counter is not only because I want to make sure it's a resilient design, but also because it will allow me to run this counter at very high speeds. That will be in service of something I want to do with this counter in the next video, and for that it is crucial that these displays run really smoothly and reliably. I noticed while I was running this that ever since I changed from the simple gear ratios to this mechanism, the units counter sometimes wasn't showing all of the numbers fully. I'm not sure if that's because of the new shifting mechanism, or just because the counter has counted up so many times at this point that some of the pieces have come a bit loose. But if it keeps being an issue in the next video, I might go back to having just that counter operating at constant speed. And as well, especially when it's sped up like this, I really don't think the hundreds and thousands displays take all that much time at all to switch between the numbers, so I'm pretty happy about that. Finally, I did want to show the counter running without the front cover on, as I think the details of all the segments toggling back and forth is quite interesting to see. And as I said, there is more to come with these displays, but that will be for the next video. So thanks for watching, and I'll see you in the next one.